Hi, this chapter is about classification. So, when people talk about machine learning, many times they talk about classification. So, think about image classification or face recognition or speech recognition. All these tasks are classification tasks. So, classification is a big part of machine learning. This is the outline of this chapter. First of all, we are going to talk about supervised learning, which covers classification and regression. So there are some basic ideas and the concepts shared by classification and regression. So we're going to talk about some basic stuff about supervised learning. And then we're going to learn three representative classification algorithms. So first one is k nearest to neighbors, and the second is naive-based classifier, and then the third one is decision tree. But when we combine a lot of decision trees, then we can make a forest. So basically, random forest is basically the same as decision tree, except that it has a lot of trees. Oh, by the way, we're gonna learn neural networks later as a separate chapter. Okay, so neural network can work as a classifier or it can work as a regressor. So it is a separate chapter. I mentioned classification and regression before, but what are they? Okay, so basically, these two are both supervised learning, and then classification predicts a discrete level of input, like face recognition. Okay, and usually it is evaluated by accuracy or so, accuracy or precision or recall or F1 measure. So there are a couple of different evaluation metrics, but most of the time accuracy is one of the most popular evaluation metrics. And it is interested in the boundary of classes. As you can see here, we have two classes, disease and healthy. And we are interested in this boundary. Okay, so if the point is in this way, then it is disease. When points are in this side, then it is healthy. Okay, so we are interested in the boundary. And the next one is regression. So regression predicts the quantity of output. So it is actually interested in the relationship of input and output. So when the input is a gene 1 and the output is a survived. Okay, or when the input is height, then the output could be weight. Okay, something like that. So we are interested in the relationship, and usually this can be evaluated by root mean square error. So how much different the prediction is compared to the label. Okay, that's what we're interested in. So this is actually represent the relationship between the input and output. Okay. And for supervised learning, there is a workflow. Okay, for training, we have a training data to train the model. Okay, so with the training data, we train the model, and now we have a trained model. And then for testing, we have a new data. We apply this model, trained model, to this new data. And then we have a prediction result. This could be classification, this could be regression, it doesn't matter. Okay, so we follow the same kind of workflow for classification regression. We train and then we apply the trained model to test the data. Okay, so let's talk about the data for supervised learning. So data is represented as a matrix or tensor. It could be a high order tensor. But let's assume that this is a simple problem. So we have a matrix. And then a row can be an observation or a data instance. And a column could be one feature or attribute. So in this matrix, we have n samples with d features. But this is not just a fixed kind of shape. Sometimes we have sample here and the features here. So when you load a data, then you have to check which dimension is which. Okay. So but recently this is more popular. So this row corresponds to the samples and the column corresponds to the features. Okay, and then usually we use X for input data. Since we have n samples, X goes from 1 to n. Okay, and then each sample X sub I has D values. Okay, which means the dimension of X sub I is D. So we have a D features. So we can have X sub I to the power of 1. It's not to the power of, but it's superscript to indicate the index of the feature. So X sub I is ith input sample with the D attributes. And Y is usually the output. Okay, and then since we have n samples, we have n number of labels. Okay, so we have n outputs. It could be classes, or if it is a regression, then it is just the value. Okay, and if it is a regression, then we can have a matrix like this. But if it is a classification, then for one sample, we have one scalar, which is the index of a class, like a 3 or 4, 1, 5, something like that. So this is for classification. But if it's a regression, we can have multiple outputs, like this. For one sample, we have multiple outputs as a vector. So this one is only for the classification problem. Okay, and the next thing is about the training and validation and testing. So we have to split the data, okay, and then we have to handle these data separately. So basically, we use training data to train the model, which means we use this training data to update the parameters. And then validation, we use this validation data to evaluate the data, okay? We don't update the parameter with this validation data. So training the parameter and evaluate the model. And then we just test the model with this testing data. If we use this testing data to train the model, it is cheating. So there is a boundary between these two. So we shouldn't use testing data to do anything about the model. As I said, the training should be done with the training data. Okay, it is learning the parameters. And then validation with the validation data is to evaluate the model. Okay, we don't update the parameter with the validation, we just evaluate. Why do we have to evaluate? So when we train the model, then how do we know how good this model is? Do we have to stop here or do we have to train further? So the validation actually evaluate the training models at every iteration or every 10th iteration. So when we evaluate the training model with validation data, then we know how good this current model is. Okay, and then if the validation data says, oh, this is the best model so far, and we don't have any hope to improve the performance further, then we can stop there, and then we're going to use that model as the best model, and then we use that model to test with the testing data. Okay, when there is no validation data, when we download the data, then many times we have a training data and the test data. We don't have a validation data, then we have to split the training data into training and the validation. And when we test, usually we predict the output of new data using the parameters learned or using the model we learned. And then, as I said, tested data should not be used in training at all. And when we don't have validation data, okay, then how can we actually split this data? So given this data, we have to split this data into training and the validation. So it depends on how many samples we have. If we don't have enough samples, then let's say 90% and 10%. But if we have a lot of samples, then we cannot have 10% because every time, whenever we evaluate the training model with this validation data set, it takes too much time. Okay, so in that case, when we have too many samples, then maybe just 1%, or it depends on the size of the data. Cross validation is a little different story from the previous slide. Okay, so when we have one data set and we want to evaluate many different machine learning models on a limited data. So in that case, we want to evaluate machine learning algorithms, machine learning models, and then we split the data into training and the testing, training, validation, and testing. And then we have to evaluate the model, and then we repeat the above steps so that we know which model would be the best on this data set. So the first method is random subsampling. So randomly, we use 90%, including this validation, 90% for training and 10% for testing. Okay. Or if you want, we can use 95% for training and 5% testing. Anyway, we can randomly sample for training and testing. Okay. Then we repeat many times. This is not the popular, okay, but the second one is more popular. We use k-fold cross validation. In this case, in this example, we have a 4-fold cross validation. So we use the first 25% of the data as testing, and the other ones for training. And in the next experiment, we use this 75% of the data samples for training and this one for testing. And in the third experiment, this one is testing, the others are training. And the last, this one is for testing and the others are for training. And when we have some limited number of samples, then usually 10-fold is most popular. And the last one, the leave one out cross validation, is only for a very limited data samples. So we don't have a lot of samples. So in that case, we just use just one sample for the testing. All the other samples are used to train the model. And in the next, we use just one sample. The second sample is the testing sample, and all the other samples for the training, and so on. So we can actually run these experiments n times. Okay, we have n samples, so we can run n times. So we can actually evaluate the machine learning algorithms on this n experiment, and then we can take an average of this accuracy or the evaluation metrics, and then we can say which one is the best model. That's cross-validation. Okay, and the next one is model complexity and overfitting. Since we just started talking about the models and training, so we have to talk a little bit about the model complexity and overfitting. So overfitting is a simple thing. So model is too closely fit to a limited set of training data. So the model is perfect with the training, but it is not perfect with the test data. So we say this doesn't generalize that well. Okay. So this figure explains what it is. First one, we have some samples. These are training samples. And then the model is too simple. So it is just linear. And when we train the model on this data set, then this line is the best line. Okay, when the model is linear, then this is the best line. But as you can see here, this model is not perfect because it's underfitting to training data. So even with the training data, there are lots of the samples with a lot of error. Okay, so it is not fitting to the training data. How about this one? In this case, the model is a little more complicated, and then in the training data, it doesn't have any error. It fits perfectly to the training data. But this is not good. Even with the perfect score with the training data, but this is not good. So let me give you one example. If the test data is around here, then the error is quite large, right? But this is not that noisy data. Okay, this shouldn't be large like this. So even though the training error is 0, but when we test, then this model is not working well. It doesn't generalize well. But if you check this model, so we have some errors here. But this is fine because when we measure the data samples, the data itself has some noise. We can just ignore this much errors. Okay, and then when we have some new tested data samples like this, then the error is much smaller than this one. Okay, so the model is fitting to the training data, but not too much. Okay, so this one is underfitting, this one is overfitting, this one is perfect. So what is the kind of good feature of the model to avoid overfitting? So first, we can spread out the probability mass from the training samples. So instead of having just a few samples, if we spread out the probability of the samples, then we can see that this smooth curve. So we can assume that the data manifold is smooth. But when we measure some samples, then these samples have some noise, so it looks like the data manifold is bumpy. But if we have a lot of samples, then probably we will see this smooth manifold. And another one is that we can discover underlying abstraction and explanatory factors. So in the bumpy data samples, these bumps are not coming from these explanatory factors. These spikes are not from the real factors. These are noise. So we can consider all these spikes as noise. Then we can focus on more abstract factors and explanatory factors. Basically, these two things are the same things, but we can interpret these phenomena in different ways. Okay. So to avoid this overfitting, there are a couple of practical approaches. First one, as I said, we need more data samples. Okay, then we can actually reduce the effect of the noise. And the second one is that we can use simpler models. So as you can see here, when the model is too complex, then there is possibility to have overfitting. But if we make a simpler model like this, then we can minimize possibility of overfitting. Or we can put some regularization. So we're going to talk about these regularizations later, but if we can put some regularizations like the model should be smooth, then basically it's the same thing, right? Or we can use early stopping. Early stopping was proposed a long time ago, but recently in deep learning, the early stopping is one of the most popular regularization trick. And early stopping is really simple. As I said, we can use the training data to update the parameters, and while we are training, we can actually evaluate the current model with the validation data set. And then, as I said, the validation data set should not be used to update the parameters, and we just evaluate. And then, when we check the performance or error of this validation data, in the beginning of this training process, it goes down. And then from some point, the validation error goes up. And this one is coming from the overfitting. So when we check the performance of the model with the validation data set, we can say this is the best model. We have to stop here. That's what early stopping does. Okay, it's a simple idea, but it works quite well.